this FET must have the depletion region. The width of the depletion region is small, but at the junction point of p-type material and n-type material, depletion region should be present due to the drift current and diffusion current. I am already discussed in the PN junction diode portion. What is the diffusion current, what is the drift current, and what is barrier potential. Due to this reason, depletion region should be present. If you apply the bias or if you apply the connect the voltage source between the base emitter junction, between the gate source junction, between the source drain junction, the width of the depletion region will be varying. Clear, Bimal?
Yes, ma'am. Yes, ma'am. Thank you.
Okay. Any question? Any question? So, before I discussing anything, you write some point regarding the FET. First, you write first point, with no external gate voltage. With no external gate voltage, that is VGS is equal to 0. And a small voltage VDS is applied between the drain and the source, and a small voltage VDS is applied between the drain and the source. Maximum saturation current IDSS will flow through the channel, from the drain to the source, from the drain to the source, restricted only by the small depletion region around the restricted only by the small depletion region around the junctions. Complete?
Yes, ma'am.
Okay. That means when VGS is 0, if we apply the VDS, that means source drain voltage, current will flow from this direction in case of N channel FET. Actually, the flow of the current through the channel is restricted or is restricted by the depletion region. That means depletion region offered the resistance or offered the obstruction against the flow of the current through the channel. So if VGS is 0 and if we apply the voltage across the source and drain, the current is flowing, the maximum amount of current is flowing through the channel. This is known as the saturation current. maximum amount of current flowing through the channel. This maximum amount of current is determined by the applied voltage VDS when VGS is equal to 0. Okay? Next, if a small negative voltage minus VGS is now applied to the gate, the size of, if a small negative voltage minus VGS is now applied to the gate, the size of the depletion region begins to increase. Reducing the overall effective area, of the channel. And thus reducing the current flowing through the channel. A sort of squeezing effect takes place. A sort of squeezing effect takes place. So, by applying a reverse bias voltage, increases the width of the depletion region, which in turn reduces the conduction of the channel, conduction of the channel. Complete?
Yes, ma'am.
That means if we apply the VGS negative, that means if we apply the gate source voltage in reverse bias condition, then we can reach the saturation current less amount of voltage of VDS. That is the less amount of VDS voltage. If you see the figure, here you see saturation current reaches less amount of VDS. And value of the, we reach the saturation current, amount of the saturation, maximum amount of saturation, maximum amount of current that is flowing through the channel, that is the saturation current is less. Okay, if we apply the VGS, when VGS is 0, saturation current is 8 milliampere. When VGS is minus 1 volt, then saturation current is, you see the graph, saturation current is near about 4.5 milliampere. VGS is minus 2 volt, saturation current is 2 milliampere. VGS is minus 3 volt, saturation current is 0.5, and VGS is minus 4 volt, saturation current is 0 milliampere. That means when VGS is minus 5 volt, minus 4 volt, saturation current 0, that means no current is flowing through the N channel, or no current is flowing through the channel of the FET. That means this is the pinch off voltage or VP. So next you write, since the PN junction is reverse biased, little current will flow into the gate connection. VGS negative means PN junction between the gate and the source is reverse bias. Okay. Little current will flow into the gate connection. As the gate voltage is made more negative, the width of the channel decreases. Width of the channel decreases means width of the depletion region will increases. Width of the channel decreases. Until no more current flows between the drain and source. No more current will flow between the drain and source. And the FET is said to be pinched off. FET is said to be pinched off. Pinched off means pinched off case in FET is similar to the cut-off region in case of BJT. Both are same thing. No current flowing through the transistor. The voltage at which the channel closes, is called the pinch-off voltage VP. The voltage at which channel closes, known as the pinch-off voltage VP. In this pinch-off region, gate voltage VGS control the channel current, and VDS has little or no effect. VGS controls the channel current and VDS has little or no effect. The result is that the FET acts more like a voltage control resistor. Which has...
Ma'am, can you repeat this line?
Yes. The result is that the FET acts like a voltage control resistor. which has voltage control resistor which has zero resistance when VGS is equal to 0 and maximum resistance when gate voltage is very negative. Under normal operating conditions, under normal operating conditions, the JFET junction FET field effect transistor, the JFET gate is always negatively biased relative to source.
Ma'am, JFET is?
Always mm, always negatively biased relative to source or relative to source. Yes, it is essential that it is essential that the gate voltage is never positive. It is essential that gate voltage is never positive since if it is, since if it is, all the channel current will flow to the gate, not to the source. The result is damage to the JFET. Complete? Complete. Biman?
Yes, ma'am?
Complete?
No, I'm writing, ma'am. 1 second.
Okay.
Yes, ma'am, done.
Done. Any doubt in this portion? I think now it is clear. If it is clear little bit. Any
Ma'am,
doubt?
ma'am,
Yes.
ma'am, can you explain why it should never be positive, the gate voltage?
Who is asking?
Ma'am, me,
Ritika.
Aritra.
If gate voltage is positive, then what happened? Positive means forward bias condition. So, if gate is positive, that means VGS, the source voltage VGS, positive terminal of VGS is connected to the positive terminal of the p-type material in case of n-channel FET, then gate is positive. That means gate source circuit is forward bias condition. If gate source circuit is forward bias condition, current will flow through the gate circuit and huge amount of current is flowing because the channel current is flowing through the gate circuit. If you see the circuit, then instead of flowing the current in this way, the current is flowing in this way because this is the positive. If the gate is positive, that means this terminal is positive and this terminal is negative. So channel current is flowing in this way. That means huge amount of current is flowing through the gate circuit. So this gate portion is lightly doped, so breakdown occurs. So it will damage the FET. Clear, Aritrika?
Yes, ma'am.
Okay. Next, one thing. Next, to write the VI characteristics of trait.
Ma'am, when VGS is negative, that means the gate will be at a lower potential than the source, right?
Yes,
So that facilitates the current flowing, right?
that's facilitated the current flowing through the source drain circuit.
Yeah.
Channel current is,
That's an ideal condition, right?
yes, you
Okay.
should
Thank
all time maintain the VGS should be 0 or you should maintain the VGS should be negative.
Yeah.
Either 0 or negative. Actually, we maintain the VGS negative. If we maintain the VGS negative, then we can easily achieve the saturation current. And saturation current level is low compared to the VGS is 0. If you see this figure, or this is for P channel. So if you see the N channel characteristics, this is the N channel characteristics card between the ID and VDS. If VGS is 0, saturation current is more. If VGS is minus 4 volt, saturation current is 0. We always maintain the VGS negative between V peak to V0, not the VP. VP means the pinch of voltage. At this point, at this voltage, if we apply this voltage, then what happens? No current flowing through the channel. So we maintain the voltage VGS in between this value, that is VP 0 volt to VP. That means 0 to minus 4 volt. Okay. Characteristics card for P channel is same, and this portion represent the breakdown region. Okay, actually I will discuss, this is the symbol of, this is the first I am discussing the symbol of, before I discussing the VI characteristics of N channel and P channel FET. You see the slide, this is the symbol of FET. This symbol represent the N channel FET. You only see the direction of the current. This is the positive terminal, that is the drain. N channel, in case of N channel, positive terminal of the VDS connected to the drain, negative terminal of VDS is connected to the source, and this is the VGS, and VGS, here VDS is showing, so this is the positive terminal and negative terminal of VDS, and this terminal denotes the negative terminal of source, not the negative terminal of VGS. Negative terminal of VGS is connected to the gate and positive terminal of VGS is connected to the source. Okay, gate is positive. In case of N channel, this is the N type material, this is the N type material, this is the P type material. So this is positive and this is negative. Okay, this is the symbol of N channel FET, and this is the symbol of P channel FET. Here you see the direction of the current. In case of N channel FET, current is flowing from source to drain because this is the positive terminal. P channel FET, current is flowing from drain to source. The direction of the current is just opposite in all the cases. Gate current is flowing in this way, gate current is flowing in this direction. Okay, this is the symbol of FET. And transfer characteristics. What is the transfer characteristic? In case of BJT, collector current, that is the output current, is the function of base current. So IC is equal to function of IB, and this is equals to IC is equal to beta of IB. This is the constant. I think whenever you studied in the transistor, Preeti ma'am will discuss. At that time, you can understand what is the beta. So IC is the function of base current. This is called current control device. But in the case of FET, you see that ID is the drain current similar to the collector current. That means ID is the drain current, means this is the output circuit current. So ID is equal to IDSS. IDSS means saturation current into 1 minus VGS, voltage between gate and source, divided by VP. VP is the pinch of voltage, whole square. Okay. This is the function of ID. So, and here you see, this is the control variable. VGS is the control variable. So, ID fully depend on the VGS. For a particular FET, VP is fixed, pinch of voltage is fixed. If pinch of voltage is fixed, if we vary the VGS, then IDSS will be vary. That means everything will be in this equation, everything will be depends on the value of the VGS. So, due to this reason, FET is called the voltage control device. Clear? Or any doubt? Why FET is called voltage control device? Is it clear for everyone?
Ma'am, can you repeat once again?
Here you see, this is the equation for ID. That is the ID means the output current, drain current. ID means drain current. If you compare with the general terminology, then this is the output current. One thing is the input, another thing is the output. In normal cases, in every machine, every devices. So in FET, ID represent the drain current, at the same time ID represent the output current. So this is the relation between ID with the VGS, VP and IDSS. Okay. If you consider a particular FET, for a particular FET, some specification should be there, and a specification means for the particular FET, pinch of voltage should be constant. If you apply the VDS equals to the pinch of voltage, for that particular FET, depletion region will touch each other and no current flowing through the channel. So for a particular FET, VP is constant. Okay. And what is IDSS? IDSS is the saturation current. And from this curve, you see that saturation currents fully depend on the VGS. If you vary the VGS, saturation current will be varying. So saturation current is also depends on VGS. That means saturation current is also the function of VGS. So in this equation, this is the constant value. This is depends on the VGS. So ID also depends on the VGS. Due to this reason, VGS means keep voltage between gate and source. That means ID, this is the output current, is depends on the voltage. So this is called voltage control device. Clear? Aditrika? Aditrika, clear?
Yes, ma'am.
Okay. You should remember this formula. Okay. This formula is also known as Shockley's equation. Okay. ID is equal to IDSS into 1 minus VGS divided by VP whole square. So from this equation, you see this graph. If we vary the VGS, then you see that when VGS is 0, VDS in x-axis represent the VDS and y-axis represent the ID. You forget about this portion, left hand side of this graph. You only consider the right hand side of the graph. And this curve shows the at various value of the VGS, what is the characteristics curves between ID and VDS. That means how the drain current varies if we vary the VDS when VGS is constant, either 0, either -1, either -2, either -3, or either -4. This curve represents that. And you see, this is the, we increase the VDS. When VGS is 0, IDS is equal to 8 ampere. In this way, when VGS is equal to -4, IDS is equal to 0, VGS is equal to -3, IDS is equal to 0.5. So in this way, we can get the curve. That means if this is the this curve is getting from the experimental value. We set the VGS value 0 to -4, and we vary the VDS, and we get the different values of ID and IDSs. If we plot, then we get this curve. And left hand side of the curve is obtained from this equation, Shockley's equation, this equation. VP for a particular FET, VP is fixed. If we vary the VGS, then we can get the IDS and ID. So if we plot this, then we get this value. And from this, if we compare these two graphs, then we see that in both the cases, saturation current is same. That means if we get the saturation current experimentally, then when VGS is 0, saturation current is 8 milliampere. If you apply the formula and if you apply the VGS is equal to 0 and VP is for a particular FET is fixed, so you can get the curve applying this 5.3 equation. Then you see that IDS is equal to, when VGS, this x-axis represent the VGS. So when VGS is equal to 0, then IDS is equal to 8 milliampere. Similarly, from the experimental, you get VGS, when VGS is equal to -1 volt, IDS is equal to 4.5. Similarly, when VGS is equal to -1 volt, if you apply, then in the equation 5.3, then you get IDS is equal to 4.5. That means either you draw the characteristics curve from the equation 5.3, or you can draw the experimentally, then you get the same results. That is, saturation current value at different values of VGS will be the same if we draw from experimental or if you draw from equation. Both gives the same result. Okay. Here, two things you will see that when VGS is equal to 0, ID is equal to IDSS. From this graph, when VGS is equal to 0, ID is equal to IDSS. Similar thing, when VGS is equal to VP, that means if you apply the VGS is equal to VP, that is a pinch of voltage. Pinch of voltage means at that point, pinch of voltage, if VGS value is VP, at that point, these two depression region touch each other and no current is flowing. That means ID will be 0. When VGS is equal to VP, that at pinch of voltage, ID will be 0. This is the two condition. By applying these two condition, we can easily draw the transfer curve from any value of the IDSS and VDSS. So when first we consider VGS is equal to 0, ID is equal to IDSS, and when VGS is equal to VP, ID is equal to 0 milliampere. VGS is equal to VP, ID is equal to 0 milliampere, because at the pinch of voltage, no current flowing through the channel. So drain current is 0. This can be achieved from this equation. Here you see the ID is equal to IDSS into 1 minus VGS by VP whole square. This is the equation 5. Sorry, equation 5.3. This is the equation 5.3. This equation is very, very important. This is the equation 5.3. So if we put the VGS is equal to 0, then what is the value? ID is equal to IDSS. Can you see? Same thing is written here. VGS is equal to 0 volt, ID is equal to IDSS. So VGS is equal to 0, ID is equal to IDSS. You should remember these 2 points. And when VGS is equal to VP, just you put the VGS is equal to VP. That means VP by VP1, that is equal to 0. So ID is equal to 0. So when VGS is equal to VP, ID is equal to 0. Another important things when you solve the numerical problem. Drain characteristics, if we substituting the VGS is equal to minus 1 volt, we know that VGS is negative. But when we put the value, you should put the sign of the voltage. Here VGS is equal to minus 1 volt. And VP is equal to VGS. VGS is equal to VP. So VP is equal to, actually in normal FET, VP value is minus 4 volt. Okay, VP value is minus 4 volt normal FET. This is the constant. So if we put the VGS is equal to minus 1 volt and VP is equal to minus 4 volt, then we get 4.5 milliampere ID. So when you put the value of VGS and VP, you should put the sign of these 2 voltage. Otherwise, if you put only the magnitude, that is the VGS is equal to 1 volt and VP is equal to 4 volt, then this result will be, you would not get the correct answer. So when you solve the numerical problem, at this, you should put the magnitude of the VGS. At the same time, you also put the sign convention of the VGS and VP. Okay, you should remember, otherwise your answer will be wrong. And if you simplify this equation, that is a 5.3, then you get this equation VGS is equal to VP into 1 by root over ID by IDSS. This is the shorthand method. If we draw the characteristics curve or transfer curve, this is the shorthand method. That means what we do, first in this case we consider that VGS to be the 1/2 of the pinch of voltage. Actually, if we apply this this assumption, that is the VGS is equal to 1/2 of the VP and ID is equal to IDSS by 2, then we can get the transfer curve very quick, and this transfer curve is nearly same the actual transfer curve. So this is called shorthand method. In this method, if we apply this method, then we can get quickly the transfer curve of the FET. So first assumption is that we assume that VGS is the 1/2 of the pinch of voltage. So just you put the value of the VGS in equation 5.3, then you get that ID is equal to IDSS by 4. After solving this equation, you get ID is equal to IDSS by 4. Another way, another assumption is that ID is equal to IDSS by 2. Then you apply VGS is equal to VP and VGS is equal to 0.3 VP. These are the 2 assumptions you take when you draw the transfer curve by applying the shorthand method. First you solve a problem, then you can easily understand the how you draw the transfer curve using the shorthand method. First you write down this problem. This is the single sentence problem. First you write down. Complete? Don't copy the solution. First, only you write down this problem. Sketch the transfer curve defined by IDSS is equal to 12 milliampere and VP is equal to minus 6 volt. Complete. Viman,
Yes, ma'am.
complete.
Yes, ma'am.
Okay. IDS is 12 milliampere means when IDS means saturation current, maximum saturation current IDSS. So IDSS is equal to 12 milliampere means when VGS is equal to 0. So you write IDSS is equal to 12 milliampere and VGS is equal to 0. Next is the VP is equal to minus 6 volt. VP is equal to minus 6 volt. When VGS is equal to VP, then ID is equal to 0. VGS is equal to VP, ID is equal to 0 milliampere. These are the two conditions you can get from the question. Next, you apply the assumptions. Assumptions means first we apply the first assumptions, that is VGS is equal to VP by 2. That is VGS is equal to 1 half of VP. When VGS is equal to 1 half of VP, that means ID is equal to IDSS 4. IDSS by 4. So here you apply VGS is equal to VP by 2. That means VGS is equal to VP by 2 means minus 6 volt by 2, that is the minus 3 volt. When VGS is equal to minus 3 volt, at that condition, what is the value of ID? ID is equal to IDSS by 4. IDSS in this condition, IDSS is equal to 12 milliampere. 12 milliampere by 4, that is the ID is equal to 3 milliampere. First assumption.
Ma'am, how did you say that VGS is equal to 0?
Yes. When VGS is equal to 0, at that time IDSS is the if you go through the when VGS is equal to 0, IDSS value is maximum compared to the other VGS's value. Okay.
So, ma'am, if it's greater than 4, then
Wait,
VGS is equal to 0.
wait. When VGS is equal to 0, at that time you get the IDSS, that is the saturation current, is the maximum saturation current.
Yes, ma'am.
Wait. So, and if you here you see when the VGS is negatively you increase the VGS value in negative order, that is the minus 1, minus 2, minus 3, minus 4. If you increase the VGS in the negative order, then IDS value will be decreasing. So in this problem here you see IDSS is given, IDSS is equal to 12 milliampere. So 12 milliampere you get when VGS is equal to 0 and VP is equal to minus 6 volt. So when VP is equal to VG, at this condition ID will be 0. These two condition we get from this characteristics curve. We get in this problem only two things are given, that is the VP is equal to minus 6 volt. Another thing is given, that is the IDSS is equal to 12 milliampere. So at what value of VGS we get the IDSS is equal to 12 milliampere? IDSS is the maximum saturation current. So when VGS is equal to 0, we get the maximum saturation current. So we here written that IDSS is equal to 12 milliampere when VGS is equal to 0. But plotting the transfer curve, Here we assume the two assumptions. First, we assume that VGS is equal to 1 half of the BP. When VGS is equal to 1 half of the BP, at that condition, ID is this. ID with the relation between ID and IDSS is this. And next assumption is that ID is equal to IDSS by 2. At that assumption, we get VGS is equal to 0.3 BP. These are the two assumptions we consider for drawing the transfer curve applying the shorthand method. But in this numerical problem, given quantity is IDSS. IDSS is 12 milliampere means when VGS is equal to 0, at that time we get IDSS is 12 milliampere. BP is equal to minus 6 volt means this is the pinch of voltage for that particular FET. If we apply VGS is equal to VP in that particular FET, then we get ID is equal to 0. So we write down these two conditions from the given quantities of the given numerical problem. But when we draw the transfer characteristics, applying the shorthand method, we assume these two assumptions. First assumption, for plotting a transfer characteristics, some point is required to draw the line. So we assume some assumptions. First assumption is that VGS is equal to 1 half of the VP. 1 half of VP, then ID is equal to IDSS by 4. So just we apply first assumptions here. VGS is equal to VP by 2. So VP by 2 means here VGS is equal to minus 3 volt. So when VGS is equal to minus 3 volt, what is the value of the ID? And when VGS is equal to half of the BP, this is the ID relation. So at that condition, ID is equal to IDSS by 4. So when VGS is equal to minus 3 volt, ID is equal to 3 milliampere, we get these two value from the first assumptions. Second assumption is that ID is equal to IDSS by 2. If we assume the ID is equal to IDSS by 2, what is the relation between VGS? VGS is equal to 0.3 VP. So applying the second assumption, ID is equal to IDSS by 2. What is the value of ID? That is the 6 milliampere. And what is the, if we assume the ID is equal to IDSS by 2, then VGS is equal to this relation. So 0.3 VP, 0.3 into minus 6 volt is equal to minus 1.8 volt. Here you see that minus 3 volt VGS, ID is equal to 3 milliampere, minus 1.8 volt VGS, ID is equal to 6 milliampere. You get the 4 point for drawing the transfer characteristics. Then you draw the x-axis and draw the y-axis. X-axis represent the VGS, y-axis represent the ID. And from the assumptions, you see that when VGS is equal to minus 3 volt, ID is equal to 3 milliampere. Just to plot, when VGS is equal to minus 3 volt, ID is equal to 3 ampere. Next assumption is that when VGS is equal to minus 1.8 volt, ID is equal to 6 milliampere. When VGS is equal to minus 1.8 volt, IG is equal to 6 milliampere. And from the given condition in the numerical problem, in this problem, when VGS is equal to 0, IDS is equal to 12 milliampere, VGS is equal to 0, IDS is equal to 12 milliampere. VGS is equal to VP, that means minus 6 volt, ID is equal to 0. VGS is equal to VP, that is the minus 6 volt, ID is equal to 0. Then you draw these 4 points, then you get the transfer curve. In this way, you can draw the transfer curve using the shorthand method. Clear or any question? Any question, Biman? If you have any doubt, you can ask me.
Yes, ma'am. It would be like very beneficial if you explain this again.
I can't hear you.
Ma'am, can you explain this again? This problem.
Okay. When you draw the curve, you need some points. Yes or no?
Yes, ma'am.
Yes. So our objective is to finding the points. How you get the points? In this problem, only two things is there. One is the saturation current is given, another one is the pinch of voltage is given. From this 2 point, from this two condition, you derive the 4 points, or you derive the 4 points which are required to plotting the transfer curve. So how you derive? Shorthand method is given to a procedure. Shorthand method describe the procedure how you get the points to draw the transfer curve. Shorthand method explain that if you first you assume that VGS is equal to half of VP. Then if you apply the VGS is equal to half of VP in the equation 5.3, then you get the ID and IDSS relation. That means applying this assumption, you get 1 point. Okay. Another point. Next, shorthand method explain that if you consider the ID is equal to IDSS by 2, then you get another point. That means then you get the relation between VGS and VP, and if you apply the put the value of the IDSS and VP, then you get the ID value and also VGS value. That means you get another point. That means in this way, applying the shorthand method, you get the 2 points which is required for plotting the transfer curve. And another 2 points. If you draw the 2 points, you can get the straight line all time. So 2 point is not sufficient for drawing any characteristic curve. More than 2 point is required. When you draw any type of characteristics curve, you should consider more than 2 points. Because in any condition, if you draw the 2 points, you get a straight line. Okay. So applying the shorthand method by assuming the some conditions, we get 2 points. Another 2 points we get from the questions. First thing is that IDSS is given. IDSS is 12 milliampere. So what condition we get the IDSS maximum? When VGS is equal to 0. So we get the another point. That is the third point. VGS is equal to 0. That point means coordinate of the characteristic curve. Okay. So we get third coordinate of the characteristic curve, that is x-axis is VGS, that is value is 0, y-axis value is ID, and that value is 12 milliampere. Fourth coordinate point of this transfer characteristic curve we get from the second clue, which is given in the equation in the problem, that is VP is equal to -4. If we apply the VGS is equal to VP, we know that when VP is equal to VGS, ID is equal to 0. So you apply this condition. So VP is equal to VGS and ID is equal to 0. This is the fourth coordinate of this point. You just draw the x-axis and y-axis and just put the coordinate and draw the and connect the 4 coordinate, you get the characteristic curve. Is it clear? Bhimal?
Yes, ma'am. Yes, ma'am.
Aritrika, Shreyoshi, Kritika, clear?
Yes, ma'am.
Yes, ma'am.
Okay. Okay.
Yes, ma'am.
Next problem. This is the next problem. Sketch the transfer curve of p-channel device. One thing you should remember when you calculate the value of VGS and IDSS, ID, etc., you should apply the magnitude. At the same time, you should apply the sign convention. Otherwise, you get the wrong value and your curve will be wrong. So you should value here, you see magnitude, at the same time sign. Here you see next problem, you do it yourself at your home. Sketch the transfer curve for a p channel device with IDSS is equal to 4 milliampere and VP is equal to 3 volt. P channel device, VP is 3 volt, because in p channel gate is n-type material. If gate is connected with the positive terminal of the VGS, then gate source should be reverse bias condition. So here VP is plus. But in case of N channel, VP should be negative. So first we apply, that means IDSS 4 milliampere means IDSS is equal to 4 milliampere when VGS is equal to 0. VP is equal to 3 volt when ID is equal to 0. Next two assumption, that is the VGS is equal to VP by 2, 1.5 volt. ID, at that condition, ID is equal to IDSS by 4, that is the 1 milliampere. Second assumption, ID is equal to IDSS by 2, that is 2 milliampere. And if we apply this value, then VGS is equal to 0.3 BP. So VGS is equal to 0.3 volt. That is 0.3 into 3 volt, that is the 0.9 volt. Just you draw the VGS. Here you see that VGS, all VGS values are positive. So axis direction should be in right hand side. So this is the VGS and this is the ID, and you just put the put the 4 coordinates, then you get the characteristics curve of P channel. Only difference thing is that characteristic curve for P channel is right hand side and characteristics transfer characteristics curve of the N channel is left hand side of the x axis, because VGS is negative and here VGS is positive. Any question? Any question? Biman? Any doubt?
No, ma'am. No.
Okay. Then you write down. So I think if it is clear for everyone. So you write down the characteristic VI characteristics or output characteristics curve of typical JFET. Output characteristics curve of typical JFET. This is the, the characteristic curve. You just write down the theory. This is the output characteristics curve of JAPT. This is for N channel. So you draw this curve, that means this curve. This curve, this is the N channel APT output characteristics curve. Okay. From the slide, you draw this curve when, if the question is comes in your exam, and just write down the theory. The voltage VGS applied to the gate controls the current flowing between the drain and the source. Controls the current flowing between the drain and the source. When you write down the VI characteristics of JFET, you should draw the circuit diagram, and at the same time you draw the characteristic curve, that is the VDS versus ID curve. Complete?
Yes, ma'am.
VGS refers to the gate source voltage, where VDS refers to the drain source voltage. Because the junction field effect transistor, that is JFET, is a voltage control device, no current flows into the gate. No current flows into the gate. Then the source current IS
Ma'am, can you repeat this line?
then the source current IS flowing out of the device equals to the drain current flowing into it, equals to the drain current flowing into it, and therefore ID is equal to IS, and therefore ID is equal to IS. Characteristic curves shows the four different regions of operation. Characteristics curves shows the four different regions of operation for a JFET. Ohmic region, saturation region, cut-off region, and breakdown region. Ohmic region, saturation region, cut-off region, and breakdown region. Complete?
Yes, ma'am.
Ohmic region. First to write ohmic region. VDS greater than 0 and VDS less than VP.
Can you repeat?
VDS greater than 0 and VDS get less than VP. That means value of the VDS lies between 0 to VP. Shubhradeep Rajra, are you hear me? Shubhradeep Hazra?
Yes, ma'am.
What is VP?
Yes, ma'am.
What is VP?
Base voltage.
VP, PP. What is VP?
VB, ma'am. Your VP.
Which is applicable for FET? VB or VC or VP, whatever you think, which is applicable for FET?
VP.
BP. So what is BP?
Pinch of voltage.
What is pinch of voltage?
Sorry, ma'am.
Yes?
Sorry, ma'am.
Why sorry? From yesterday, I am repeatedly telling that what is BP. Today's class, I think at least 10 times I am telling that what is BP. You are not present in the class. And at the starting of this class, I am writing the what is the BP. I am dictating you. Biman, what is BP? Shubhradeep has to hear, carefully listen what Biman says.
Yes, ma'am.
Biman, what is BP?
Can you hear me, ma'am? Hello.
What is BP?
Yes, ma'am.
That means what is pinch of
Ma'am,
voltage?
ma'am, VP is pinch of voltage, ma'am. Ma'am,
What?
ma'am, when
Yeah,
VDS is like increased, then it results in the two depletion regions in the N channel to like touch each other. So this is referred to as a pinch. This touching of the two depletion regions is referred to as a pinch, and the level of VDS that makes that ensures this touch is known as the pinch of voltage.
that means at that condition, drain current or channel current is zero.
It should be zero, but it's not zero, ma'am.
Actually, in practical case, this is not zero, but in theoretical condition, this should be
Should be
zero.
yes, ma'am. Yes, ma'am. Should be zero, but it's not zero.
Then, Shubhradeep, what is pinch of voltage? Actually, many of people are joining the class for attendance, and you think that exam will be held in online mode. So I will copy from the PPT or from the book, then I will pass. So write the ohmic region. Ohmic region means VDS is greater than 0 but less than VP. In this region, channel depletion layer is very small, and the FET acts as a variable register. In this, the VDS value is greater than 0 and less than VP, or in this region or in this mode of operation, the VDS value is greater than 0 and less than VP. So, there is no pinch off of the channel. So, there is no pinch off of the channel. And the current ID increases. If you see the VI characteristics card, then you see that in this region, current is increasing. when we increase the gate source voltage VGS, when we increase the gate source voltage VGS, the channel conductance falls, and the resistance is increased. Therefore, the depletion regions will spread more. Depletion region will spread more, makes a channel narrow. The channel resistance changes generally from 100 ohms to 10 kilo ohms. And obviously controls the voltage. Hence, transistor acts as voltage control resistor in this region. Complete? Aritrika, complete?
Yes, ma'am.
Okay. First, you go through this para, and if you have any doubt, you can ask me. Then I go to the saturation region. All of you go through this para. That is the ohmic region. If you have any question, any doubt, you ask me. Why cannot we give positive VGS in JVT? I think Shubham. Shubham, I noticed that you yesterday and also today, and maximum number of class you join the class near about 9:40. Why? Plus, first you tell me. You were the last person who joined this class. No, sorry. Sorry is not the answer. You repeatedly joined the class, last person. If you join the class last, as the last person, then how you can understand this type of problem? Aritrika asks this question first. In the middle of this class, Aritrika again asks this question. And your question is not correct. You write in this chat box that, ma'am, can you explain again? Why can't we give positive VGS in JFT? In case of P channel, VGS is positive. So your answer is no, your question is not correct. In case of N channel, we apply the negative VGS. Why? In case of P channel, JFT, why we apply positive VS? Diode resistance is low. Inside the resistance of the diode is low. Similar thing happened in this case also. If N channel FET, in case of N channel FET, first you tell me that, Shubham, first you tell me, in case of N channel FET, gate is p-type material or n-type material? Shubham, we can apply only 0.75 to 0.7 volt positive volt after that device burst. I think you are in the PN junction diode condition. This is the FET. Doping characteristics of the FET is totally different bit of the PN junction diode. If FET, if BJT, if PN junction diode, both are all are same thing, then why we use the BJT and FET? We only simply use the PN junction diode. First, you tell me in N channel FET, gate is p-type material or n-type material? First, you tell me. You write in the chat box first. N channel FET gate is p-type or n-type? P-type. If p-type metal is connected with the positive terminal of the source, then this is forward bias or negative reverse bias? Shubham, please write in the. If p-type material is connected with positive terminal of any DC source, then this is forward bias condition or reverse bias condition? What happened? Write in the chat box. Shubham. Forward bias condition. In forward bias condition, current will flow through the diode. Similar thing happened. If N channel FET gate is connected with the positive terminal of the VGS, then gate source should be forward bias condition. So all the channel current will flowing through the gate. If all the current is flowing through the gate, what happened? Gate will be breakdown and total damage occurs. Clear? So next you write down the saturation region. I think Shubham, it is clear for you? Shubham? Okay. Saturation region. In this region starts from the points. This region starts from the point where VDS is greater than VGS minus VP.
Well, VDS is
Greater than VGS minus VP. Here Vp is the pinch off voltage and VGS is the gate source voltage. In this region, the drain current ID entirely depends on VGS. In this region, gate current, drain current ID entirely depends on VGS and not a function of VDS, drain source voltage, and not a function of drain source voltage, VDS. The FET operates in this region. The FET operates in this region to amplify the signals as well as for switching operation. Amplify the signals and as well as switching operation. From the figure, it is observed that when VGS is equal to 0, in the figure, it is observed that when VGS is equal to 0, the maximum current ID flows. Maximum current ID flows.
Ma'am, can you repeat?
From where? From
Ma'am,
the figure. Yes. Yes, Kritika.
Yes, ma'am. Repeat.
Repeat from. Okay. From the figure, it is observed that when VGS is 0, the maximum drain current ID flows. Maximum drain current ID flows.
Ma'am, do we need to draw the figure?
Yes, you should draw the circuit diagram as well as the characteristic curve. You should draw these two figures. This figure, this is the characteristic curve, and this circuit. This circuit here you draw. Instead of this circuit, you can draw this circuit. This circuit. This is the circuit diagram. Okay. You draw this circuit diagram as well as this is the figure number 5.4, and you draw the characteristic curve, that is 5.10. When we change the VGS mode negative, when we change the VGS mode negative, the drain current is falling. The drain current is falling. At a particular value of VGS, The drain current flows constantly through the device. Drain current flows constantly through the device. Hence, this region is also called constant current region. Hence, this region is also called constant current region. Complete? Cutoff region, VGS is less than VP. Cutoff region, VGS is less than VP. This is the region in which drain current ID is 0. This is the region in which drain current ID is 0 and device is off. In this, the gate source voltage VGS is less than pitch. This means the value of VGS is more negative than VP. Value of VGS is more negative than VP. Therefore, the channel closes and does not allow any current flow through the device.
Ma'am, after therefore?
Therefore, channel closes and does not allow any current flow through the device. Complete? Complete. Shumon Banerjee, complete.
No, ma'am.
Next point is the breakdown region.
Done, ma'am. Done.
Done, okay. Next is the breakdown region. The voltage between drain and source, that is VDS, Breakdown region means this region. This region. If we apply the VDS more and more, then what happened? Total breakdown occurred. So this is called breakdown region. So if VDS is high enough to causes the JFT's resistive channel, JFET apostrophe S, JFT's resistive channel to and pass uncontrolled maximum current
Ma'am, can you just repeat?
If the voltage between drain and source is high enough to causes the JFT's resistive channel to break down, JFT's resistive channel to break down and passes uncontrolled maximum current. This is known as breakdown region.
Ma'am, can you repeat from the start again? If the
If the VDS is high enough, to causes the JFT's resistive channel, that is the in case of N channel, in case of P channel FET, that is a P channel, is resistive channel to break down. Resistive channel to break down and passes uncontrolled maximum current. You see this figure, then you can easily understand. This is the figure. In this case, if VDS is high enough, that means the channel, this channel will be break down and uncontrolled maximum current is flowing through this circuit. Both the cases happen in case of N channel type, in case of P channel type. So this known as breakdown region. Any doubt? Any question? VI characteristics of FET. This is the last class for FET. From next Tuesday, I will start MOSFET. So from this note, you see that FET acts as a switch. So if question comes that how FET acts as a switch, then you can write the answer. Yes or no? During the ohmic zone, current is flowing. During the saturation region, current is constant. During the cutoff region, no current flowing. So FET acts as a switch. So first I am this is the modified FET note. Some portion is added in the last few slides. You go through this, and you also Aritrika and Sevsri. Anyone from you can upload this your official WhatsApp, unofficial WhatsApp group at the same time, Google Classroom. Last few slides are added. Aritrika, you got the fate modif.
Yes, ma'am.
Okay, you upload in your unofficial WhatsApp group at the same time in the Google Classroom. Okay. Today is 14th, 15th. Okay. Akash Dotto, present. Aritrika present. Atanu Shana present. Bimayan present. Devabroto Sil present. Kritika present. Man Bharma present. Pritam Shi present. Priyangshu. Priyangshu, are you present in this class?
Yes, ma'am.
Present. Roman Bhaduri present. Shreyushi present. Shubhadeep Gop. Shubhadeep Gop.
Yes, ma'am.
Shubham Roy present. Shubhradeep Hajra present. Shumon Banerjee
Present, ma'am.
present. Only Akash Datta absent. Okay. You may leave the class.